welcome back. So today is the concluding lecture for compound semiconductors. If you recall, in the last class we had finished up the concepts of MOSFET, HEMT, and also discussed about gallium arsenide, LGAS devices where they are used, the band diagrams and other advantages and so on and so forth, including HBTs where you can get a sufficiently high gain. I told you that today in the last lecture for compound semiconductor we will discuss about III-nitrides, which is a very dominant semiconductor technology, and you will see why. People often say that III-nitride or gallium nitride based technology is the second most important technologies in semiconductor after silicon, even more important in gallium arsenide because of the wide range of applications it has and the large market that it actually enables. Okay, you will be surprised that gallium nitride white LED market is more than $14 billion, which is a huge market. All the white LEDs that you can see off the shelf that you can buy in Big Bazaar, I keep telling you, is actually made of gallium nitride technology only. So today we shall see why gallium nitride is so important and what are the basic essential things of gallium nitride technology. Excuse me, sorry. Okay, so in gallium nitride technology, when I say, so we'll come to the whiteboard here. So when I say III-nitrides, okay, when I say III-nitrides, it essentially means three compounds: gallium nitride, aluminum nitride and indium nitride, and these binaries can combine to give you alloys as well. So for example, aluminum gallium nitride or aluminum indium nitride can be made, or indium gallium nitride. So these alloys and these binaries together form the III-nitride family of semiconductors, and this III-nitride family of semiconductor is completely direct band gap. Okay, it's completely direct band gap, which means they can absorb and emit light, and it enables a huge range of band gap. Indium nitride, for example, has a band gap of 0.7 eV, gallium nitride has a band gap of 3.4 eV, and aluminum nitride has a band gap of 6.1 eV, which you can call to be like insulating, but this can be n-type doped, for example, and so you can change the conductivity, hence it's a semiconductor. In a way, you can span the band gap from 0.7 eV to 6.1 eV, which is it's almost like near IR, okay, near IR to mid IR in this thing, to this is 200 nanometer, which is deep UV. So you can span the entire optical up to UV and deep ultraviolet as well as near infrared, almost on the borderline of mid infrared. So this is a very unique kind of a property of this family of semiconductor, that it has a direct band gap and it has such a large range of band that you can actually enable by alloying and making heterostructures. Of course, for optical devices it's a very big benefit, but also electronic devices can benefit from this kind of band gaps. You will see why. Okay, all these materials have to be grown epitaxially, which means either you have to do MBE or MOCVD to grow them layer by layer at the precision of an atomic thickness, as I keep telling you. And the beauty of this material system is that they are polar materials. What is polar material? Polar material is these are polar materials, and unlike silicon or gallium arsenide, which are not polar, gallium nitride and its family of compounds are polar material, which means each unit cell has a dipole. Okay, each unit cell has a dipole, and that means you will see that if you take a slab of gallium nitride, any thickness of here, then each unit cell actually has a small dipole attached to it. So there will be a sheet of negative charge at the top and a sheet of positive charge at the bottom. It can sustain electric field. This kind of behavior, and this is in a spontaneous condition. This is without any application of field, without shining light, nothing. Okay, in equilibrium. So this is a very unique sort of a thing that you take a piece of gallium nitride and there is a charge at the top and the bottom. This is called this is because the unit cell with the unit cell of this, actually the crystal structure of gallium nitride is woodsite, and woodsite is essentially like a distorted hexagon, and because of that this material does not have a center of inversion symmetry. What does it mean? What it means is that if you take a piece of silicon, for example, okay, if you take a piece of silicon or if you take a piece of gallium arsenide or anything, right, if you take a piece of silicon, if you flip it upside down, that means if this is the top surface and this is the bottom surface, if you flip it upside down, nothing will change because this is the same plane. Whether it is 111 or 100, it will always remain the same unless you cut the crystal in some direction. The flipping upside down doesn't have any problem. But over in gallium nitride, flipping upside down actually will have different properties because of this polarization, that there is a sheet negative charge at the top and sheet positive at the bottom. So when you flip it upside down, if you flip it upside down and this is gallium nitride, then sheet positive will come at the top and sheet negative will come at the bottom, and this is why it makes it, it doesn't have an inversion symmetry. It's not the same when you flip it upside down. And where does this charge come from and what is this polarization? that we'll discuss. Of course, this is a very unique property. I told you this is not present in many of the other common semiconductor like silicon and gallium arsenide and other things. And apart from this polarization, gallium nitride has a huge range of band gap, as I told you. So this makes it very unique, and it has a lot of properties of material which cannot be found in other systems, and you will see why heterostructure based on this are unique, because now they are polar, they have an inbuilt field. So even if you are applying electric field outside, you will see a very strange kind of a band diagram here. Okay, so that's what I told you. Let's, before I go to the unit crystal structure and the polarization, I'll still revise a little bit here, that gallium nitride and aluminum nitride and indium nitride can enable a large range of band gap here. And this is why it has been very promising. It has enabled the blue and the green LEDs, and laser diodes are something that only gallium nitride technology has enabled efficiently. Before the advent of gallium nitride in 1990s, people couldn't get blue emission, and it was very inefficient, and green was also terribly inefficient, because green is typically 500 to 550 nanometer, blue is around 420 to 480 nanometer, also almost bordering violet here. But this kind of wavelengths require larger band gap, and there was no semiconductor. For example, 2.4 eV, 2.9 to 3 eV, these are required for green, this is required for blue. There was no semiconductor that would operate in this that would have a band gap of such large band gap. People are investigating zinc oxide and some other materials, but there is a lot of problem with p-type doping. So finally people had discovered, people had made advances in gallium nitride technology, and now this enables you to get this band gap. So how would you get a band gap of, say, you want blue, for example, you need 2.9 eV, and that is your blue. How will you get this blue? The way you will get this blue is that you will have to mix indium nitride and gallium nitride. You see, gallium nitride has a band gap of 3.4 eV, and indium nitride has a band gap of 0.7 eV. So I told you, if you mix a little bit of this and a little bit of that, so for example, if you mix around 5 to 10% indium nitride and 90 to 95% of gallium nitride, for example, you will get something like, say, indium 10, gallium 90, and then nitrogen. This will probably have a band gap of around 450 nanometer, corresponding to a wavelength of 450 nanometer, which will emit blue. So this blue LED that you get, if you cover it with a phosphor coating, I'll come to that maybe in the LED lectures later on. If you cover it a phosphor coating, this blue gets shifted to, and it also emits an yellow, and the both of them mix, the blue and yellow part will mix to give you a sensation of white. Okay, that's how white LEDs are made. Mostly they are made. So if you look at a LED bulb, if you stare it carefully, you will see that it has although it is white, it has a slight bluish tinge. You will look it today only. Okay, you will see a slight bluish tinge. That is because it is a blue LED that has a phosphor coating to convert it into a white LED, right? So you have to mix and match indium, around indium 10%, gallium 90%, for example. If you want to make a green LED which emits at, say, 540 nanometer, that is green, then maybe you have to have probably indium of around 0.25%, gallium of around 0.70, 25% gallium, 75%, that will probably emit in somewhere around green. So that you can tune the band gap. Of course, you can argue that you can also mix aluminum nitride and indium nitride, but that is a little bit more difficult from the materials point of view. See, these materials, when I say you are mixing and matching to form alloys, there is a lot of material science that goes behind it in terms of lattice mismatch and the difficulty in growing the material in the system. Typically, indium and aluminum nitride and indium nitride, mixing them together has not been so widely studied, because it is little difficult to grow aluminum nitride. It is also little difficult to grow indium nitride. Gallium nitride has been more widely studied, and gallium nitride based things can be more easily grown. So gallium nitride mixed with aluminum nitride and gallium nitride mixed with indium nitride are more widely studied, rather than aluminum nitride mixed with indium nitride, although that also can be done. Okay, so this is the broad picture of III-nitrides. Now if you come to the unit cell, I told you that gallium nitride has a little bit of an hexagon sort of a thing, but it's a distorted hexagon. So although it looks like a hexagon, it's slightly distorted from hexagon. And what happens is that because of that, and because of another reason, which is that this is the gallium nitride tetrahedral unit cell structure. So if one gallium atom will be bonded to 4 nitrogen with because of this sp hybridization, and each of these gallium nitrogen bonds here actually they have, because of a large electronegativity difference, the electron cloud will be shifted little bit asymmetrically. The electron cloud will be shifted little asymmetrically. The electron cloud will be more towards nitrogen and less towards gallium because of a large electronegativity difference. So there will be a resultant polarization along this bond because it's like a dipole now, and the in plane polarization, the total in plane polarization will cancel each other, but the vertical polarization in the z direction, this is the growth direction, okay, the in plane polarization will cancel each other, but the vertical in the direction, the dipole will not cancel each other. The dipole will not cancel each other, so it will behave like there is a delta negative charge at the top and delta positive charge at the bottom. So of course unit positive charge will try to move this way, so the field will actually point in the upward direction, which means in the convention there is something called polarization in this material. That's why the polarization will point in the direction opposite to the field. So the electric field will be in this direction and the polarization will be in this direction. What is polarization? That ability of the material to to polarize. Basically it's a dipole there, right? So there is a negative sheet charge at the top, the positive like a delta charge at the bottom. So this dipole results in polarization, and you see the direction of the field is towards the top and the direction of polarization is in the bottom. So this unit cell itself is polar, and that's why it has a dipole, it has polarization. Okay, and what happens is that if you take, and of course one unit cell is nothing. To get any layer you will have many unit cells, many layers of gallium nitride. So you have one unit cell, one layer, then on top of that you have another layer, you keep growing like this, only then you will get a thick layer of gallium nitride, whatever, 10 nanometer, 100 nanometer, 1 micron, whatever. So at every positive, every top interface you will have a negative charge, at the bottom interface you will have positive charge, negative, then positive. So all these will cancel each other eventually, the interfaces. What remains is that at the bottom you will have one delta positive charge here, you will have one delta negative charge here. So that's called polarization. And what will happen is that you will have to draw the band diagram taking that into consideration. So if you take a piece of gallium nitride like that, there will be a sheet of charge here like that, and there will be a sheet of charge here like that. This charge, please remember, this is not a mobile charge. It's not like a mobile electrons and holes that you can use to conduct electricity. It is not mobile charge. It is also not like a fixed ionized donors or acceptors sort of a charge. Okay, it's not like a fixed ionized donor acceptor sort of a charge that you can get after doping or something. There is no doping here. Please remember, there is no doping here, but because of this polarization you will be able to get a transistor even without doping, which is not possible in other semiconductor, right? You cannot have a transistor without doping, right? But in gallium nitride you can have that because of this polarization. It's an extra degree of freedom. This polarization gives you an extra degree of freedom. So what this charge is essentially is that it's a dipole charge. Okay, it's like a dipole charge. Okay. Okay. So now if you draw a band diagram of this, of course in equilibrium your Fermi level has to be constant, but what will happen is that because of this negative and positive, the band diagram will look like this. Okay, it will look like this. But of course if you keep growing it thicker and thicker, then eventually your this is the valence band, this is the conduction band. This valence band will approach the Fermi level, right? And it cannot cross this, because then you will get, what will happen is that you as soon as it approaches this and touches this, you will generate holes, and you will, of course this will also touch here because it's the same slope. You will also touch electrons here, and these electrons and holes will essentially screen out, they will screen out the field. Okay, they will screen out the inbuilt field. So you cannot keep growing it, this valence band cannot go like this, it cannot go like that. Okay, that is not possible. It will get pinned here because you will get very large density of holes and very large density of electrons that will essentially screen out the field. So what will eventually look like this is that this is your Fermi level, and you will, after that it will go like this. Okay, if the entire band gap will drop here, and after that, so only up to certain thickness you will have that field, that is a critical thickness, T critical, and for gallium nitride probably that is around 20 nanometer or so, if I recall correctly, or maybe even less. But again this assumes that in the surface there is no impurities or states, but in gallium nitride technology typically there is always surface states. These surface states are essentially like, on the surface you have traps and donors acceptor kind of levels, which will have different kinds of effects. So one of the effect is that because of the surface states or traps, they will pin the Fermi level, which means they will fix the Fermi level at one point and not allow it to go too much the entire band gap. So what will happen is that if this is a Fermi level, then it will get pinned at some value here. So instead of the whole band gap dropping, you will drop only some part of band gap, because these traps are pinning the Fermi level. The Fermi level is not allowed to move. Physically, what it means is that there is a large number of electrons or holes that these traps can donate, and Fermi level will like to move, be around that, because if the Fermi level tries to move, this extra charge, then these traps will essentially either donate or take electrons away from the Fermi level to make sure that the Fermi level is at this position. Okay, this is called Fermi pinning. Anyways, this is not so important from this course point of view. I just told you that you should be aware of. Now, how do this material enable technology? So one of the important thing is that, one of the very big thing is that it makes you white LED. Okay, white LED essentially is a PN junction of gallium nitride, and in between you will have quantum well. When you discuss LEDs, we will come to that. You know, your active layer, if you have a PN junction like that of gallium nitride, it will look like this. But as this is P, this is N. But I told you that when you are injecting, when you are injecting holes from here and you are injecting electrons from here, they are expected to recombine, but their diffusion length might be more, which means they will have to diffuse along before even one electron ion hole recombines. Also, they may move fast, so then they will not get much time. So one of the approaches in LED designs is that you don't have this kind of thing. What you do is that you enable them to recombine even more efficiently. So you have a smaller band gap material there, like that. I'm not drawing it well, so let me draw it again. So you understand, right? If there is a PN junction, just like a PN junction like this, the holes that go this side and electrons that come this side to this side have to recombine in the depletion region, but their diffusion lengths are longer. So they have to diffuse much longer, much more than this depletion region to even enable recombination. So it leads to inefficient recombination. Also, they can move very fast and might not get time to recombine. So what you do is that this is a Fermi level. You have a quantum well in between, a narrow band gap material in between. So this is your N type gallium nitride, this is your P type gallium nitride. In between you have a narrow band gap material, which can be say indium 10%, gallium 90%, because this is InGaN, and this will band gap will be say for example 3 eV. I'm just telling you, this will be 3.4 eV, this is 3.4 eV. Okay, and this is inside is 3 eV. So what will happen is that when holes come, okay, when holes come, they will fall back here and they will not be able to go out because there is a barrier here. Similarly, when electrons go this side, if they fall back here, the electrons will be here, they will not be able to come out easily because there is a barrier here. So electrons will spend more time in the well, holes will spend more time in the well, they will get more time to recombine, and then they will emit light. Okay, H nu, then they will emit light. Radiatively they have to recombine, of course, and because this layer is a wider band gap material than this, the wavelength of light emitted will be such that the energy of the photon will be less than the energy here. So the photons will not be absorbed here or absorbed here. If you have the same band gap material like this, then the photon that comes out here has the same energy as this. So this part will absorb and kill the photon, this part will absorb and kill the photon, so that reduces efficiency. So you have to get something like that. So essentially a white LED is made of a PN junction of GaN with indium gallium nitride quantum well. Okay, that is your white LED. But of course I told you, because these materials are polar and there is a field, so this InGaN, this InGaN has a huge field, and that is not good for the device, right? So for example, you will have a huge field actually, like something like this maybe. Okay, even in equilibrium you will have something like this. You don't want this field. What you want is that you do not want the extremely high field in InGaN, because there will be a sheet of negative and sheet of positive charge. So these polar materials are not the best materials for making LEDs, but people use them. But nowadays they are going to, if you have a gallium nitride crystal like this, right? I'm not drawing it very well, I'm just telling you, it's just a unit cell. Okay, if you have a gallium nitride crystal like this, then the thing is, this is a C direction, this is the growth direction, which is called C, and this is a Woods edge. So the direction convention is 0 0 0 1. Okay, that is this direction, and this is polar direction, and so you have a high field. So what people do is that they take other planes, they look at this kind of plane. So instead of looking at this plane, the top, you are looking at this plane, for example. That is called non-polar. It doesn't have polarization, because you are looking at this direction. You will make an LED on this direction. It might be a little difficult for you to understand, but you don't worry about it. But there might be also planes that go like this. You might slice the crystal such that this is your plane on which you make devices. Those are called semi-polar. they also have very negligible polarization or almost no polarization. This is semipolar. There's a lot of research on semipolar green LEDs and so on. You essentially slice the crystal in this direction and make the device there instead of making the devices on this top. Okay. So these are called different planes, and LEDs and other things, the optical devices work better when you have your devices on the nonpolar and semipolar planes. Okay. So that is all about your LEDs and gallium nitride based LEDs. But of course, gallium nitride base has many other technologies apart from the white blue LED. It can also make green LED, as I told you, and green laser diodes that are very useful, and those are used, and these are also in GaN, by the way. In GaN you can change the X here. A lot of materials and device researches keep going on in this in different parts of the world. It's a lot of advanced research going on even now for green LEDs and laser diodes. And then there is there's also electronic devices based on this. There's also electronic devices, which is essentially transistors. Electronic devices are transistors. If you remember your gallium arsenide technology, it looks like this, no? If you remember, this is your aluminum gallium arsenide layer, which was sort of doped, and then there was a spacer layer which was undoped. Okay, and this, the donor levels here will donate the electrons, and these electrons will come here and from the electron gas. You remember that? Now the best thing about gallium nitride is you don't have to dope it because there is already polarization. Okay, there is already polarization. The polarization that exists on gallium nitride and its sister compounds, aluminum nitride, AlGaN, InGaN, whatever, without any application of bias, without anything, is called spontaneous polarization, because it exists just like that, right? It exists. So instead of this kind of a structure, and this was L gas gas, by the way, right? This is like L gas, which is N minus dope, then L gas that is undoped, which is this layer, and then there is gallium arsenide. Of course, on top of that you have an N plus layer where you put source, N plus layer where you put drain, but you have to etch that away, so the gate is here, right? Now in case of AlGaN technology, you do not have to do even a doping. It's a very fantastic kind of a thing. What you do is that you just have aluminum gallium nitride, okay, and this aluminum could be around say 20%, gallium could be say 80%, and then you have gallium nitride bus. That's it. That's it. You don't have to do anything. No doping, no N plus contact, nothing. What will happen is that, if you draw a band diagram, we'll not go into the details of how to get this, but this is what happens. Because of the polarization, you will get an electric field like this. Of course, this is delta EC, and it will go like that. Okay. Okay, it will go like that. Okay. So this is your AlGaN, this is your GaN, and there will be huge 2D electron gas here. This 2D electron gas is very, very high density. This could be at least 10 to the power 13 per centimeter square, which is not possible with silicon based MOSFET or gallium arsenide based devices equilibrium. It can be even, depending on the design, it could be even 2 into 10 to the power 13, which is insane, very high, very, very high. So they can carry very high current. Because this is very high current, very high density, they can carry much higher current than gallium arsenide or silicon, and that has its own advantage. You can operate the device to get much higher current. So even a smaller area can give you higher current, you can reduce the size of the area of the device, and you can also get higher current. Matlab, you can also get a higher RF output power, for example. All these things, advantages come. Okay, smaller device footprint, higher power, and so on. But you see, there is no doping here. This bending of this field that is happening is due to polarization. You can think, because there is a negative charge here, there is a positive charge here. Okay, and this is thick gallium nitride, so that dipole is screened out mostly. So this is that, because of this field you get this very high density of electron gas. It is not because of doping, there is no doping, and physically the electrons come from the surface states. So on this here, this is a Schottky barrier height, by the way. There are surface states here. This surface donor like states, actually they are called donor states. They can donate electron. So these surface donor states donate the electrons, and they are actually accumulating here. So there is no doping, and the polarization is not the source of the electrons here. Please remember, polarization assists or enables the electrons to be here. Polarization assists, so you don't have to dope. Physically the electrons come from the surface states. Okay, and you don't have to do any N plus layer here for contact, because if you put a metal here like a source, okay, and you put a drain here, you anneal at very high temperature. like 850 or 900, depends on the metal of course, then this metal will, and you see this electron is here, no, this electron gas, which is essentially this is this very high electron density gas. Okay. So if you anneal the very high at these metals at very high temperature anneal, they will spike, metals will spike below. So they will basically touch this and touch this. So you will have a current between source and drain. Now you put the gate like this, you don't even have to put a dielectric, that's it. This is your gallium nitride transistor. Okay. Now this aluminum gallium nitride, I told you is around 20% aluminum, 80% gallium. Typically the thickness you can vary, it's around say 20-25 nanometer. And when you grow aluminum gallium nitride on gallium nitride, if you recall, aluminum gallium nitride has a lower lattice constant, smaller lattice constant. So if gallium nitride is like this, spacing of the atoms, okay, then aluminum nitride is actually smaller. So when you grow aluminum gallium nitride on gallium nitride, it tries to mimic, so there is a stress, it's called a tensile stress, because your aluminum gallium nitride atoms of this layer are pulled outside to accommodate to the gallium nitride below, and because of this stress, if there is a stress, because there is a strain, no, it's called because of the lattice mismatch, there is this strain, and because of that there is an extra polarization that comes out, it's the strain related polarization or stress related polarization, we call it piezoelectric polarization. You might have heard this word piezoelectricity. It's called piezoelectric polarization because it arises from the strain in the top algan layer, and this strain in the top algan layer happens because the lattice constants of algan and GaN are different. So the algan layer is tensile stressed to gallium nitride below when you grow. If you grow too thick, if you grow like 100 nanometer, then this algan layer will crack because the tension will be relieved. So it will crack and your device will not work. So that you don't want to go too thick. Even 30 nanometer, 40 nanometer is risky, it will crack. So you keep the thickness lower than the critical limit at which it will crack. It will crack because it's a high stress it will develop. You want to keep the stress reasonably within the critical limit. So because of that, the algan layer will have a piezoelectric component of polarization that exists along with the spontaneous polarization, and both of them will point in the same direction or will reinforce each other's magnitude. The spontaneous polarization always exists there, and this piezoelectric polarization comes because of strain, and this piezoelectric polarization of course doesn't exist in gallium nitride here because the gallium nitride is not strained as such. I am assuming just a freestanding substrate. Okay. So this piezoelectric polarization will make sure that this electron gas density is extremely high, and that is the reason you are able to get 10 to the power 13 per centimeter square or more than that. Okay, this piezoelectric polarization will make sure that you get very high density. Okay, so your algan has been stressed here. Okay, and this polarization is actually enabling you to form this electron gas without doping, which is beneficial to electric devices. But as you might have seen in the InGaN, this is not beneficial to a optical device because of this extremely high field. Your electrons will be here accumulating here, your holes will be accumulating here. So the emission of the wavelength will correspond to only this gap instead of this gap here. So what will happen is that the actual wavelength that you emit is actually a longer wavelength, it's a redshifted than what you actually expect. You see my point? It's like you have this quantum well, okay, you have this quantum well, this is the band gap, you expect to emit between two layers here, but if this quantum well becomes something like this, then electrons will be here, holes will be predominantly here because the field will push it here and here. So what you emit here is only this much, can you see that? Is only this much, which is much smaller than this. So you get a longer wavelength, it's a redshift, you don't want that. That's why in optical devices polarization is bad, you go for semipolar, nonpolar. But in electron devices like HEMT, high electron mobility transistor, you actually love the polarization here because it enables you to form a high density of gas here. Now I will not go into the details of working of this device. It's a transistor, you see that there is a source, there is a drain and there is a gate, and this is the electron gas that you essentially modulate here, right? This is the electron gas that you modulate here. Okay, and it's very high density. I'll just tell you the applications. This gallium nitride based HEMTs are now increasingly entering the market and giving a tough competition to silicon in two areas. One is called RF electronics, okay, RF electronics, and one is called power switching electronics or power electronics. Okay, so in these areas there are, see, in this area of RF electronics you also have silicon and you also have gallium arsenide technology. Gallium arsenide is for super high speed, very high frequency, but the power output it can give is much lower of course. Silicon, because of its cost advantage, it is there, but the performance is not up to the mark as gallium arsenide definitely. Now gallium nitride is coming there and it can work at very high speed because, and it's a high wide band gap material, so it can go to much higher temperature because it's a wide band gap material, so high temperature electronics is possible. It also has very high charge density, so and 2 dg, so its mobility also is high, around 2000, not as high as gallium arsenide, but it's okay. It has also high velocity, so you can make a very high density current can go, so you can make smaller devices, which are lightweight. It can also take much high current. It can take much high current. It has polarization, so you don't need to dope. It can take much high current, so you can make smaller footprint devices which are more efficient also. Okay, it has a one of the advantages that because it's a wider band gap material, its breakdown field is very high. Which means you can operate the device at much higher voltage. That means you can also get much higher RF output power. Okay, and this is much better than in gallium arsenide. Of course, gallium arsenide has a little advantage of speed. Still, gallium nitride is now widely used in strategic sector like radars and missiles and all in the advanced countries, in US and Japan and all. Their technology is used. Power electronics is another area where you have to essentially block a very high voltage. We will come to all this little bit, we have a couple of lectures on different kinds of transistors and their applications. I will tell you. You essentially have to block very high voltage, say 600 volt or 1200 volt, and when you block, you have to allow very small current to pass, and then this is the off state, and in the on state you want very high current to flow, like 10 ampere or 20 ampere current to flow at very little voltage, like 0.1 volt or so. In that kind of power electronics, gallium arsenide doesn't exist. There is silicon, of course, and there is something called silicon carbide. I didn't go to that. And then there is gallium nitride. So these technologies compete with each other. Silicon competes because of the cost. Performance may not be as good as GaN. Okay, GaN can actually switch faster. It can also go to much higher breakdown voltage, so you can block higher voltage. You can switch faster because mobility is better in gallium nitride than in silicon or silicon carbide, so it can switch faster. So these are some areas where gallium nitride based device technologies are entering the market. Of course, there are other technologies like silicon carbide, which is also a compound semiconductor technology. Its band gap is 3.4 eV, that is exactly as that of gallium nitride. But gallium nitride has more of material properties problems. Gallium nitride freestanding substrates like silicon wafer you can buy. A pure GaN wafer is difficult to grow, so it's also very expensive. You cannot make large scale devices. Commercialization. You grow gallium nitride on something which is very cheap. And so the gallium nitride has to be grown on top of silicon for these power devices, okay, mostly, and this makes it very cheap. But the problem is silicon is a different material and gallium nitride is different material, so the materials growth has enormous challenges that people have been trying to address for a really long time. There has been sufficient advancement. You can get good quality of gallium nitride on silicon, but nowhere near the quality of gallium arsenide wafer or other things. So that's why there's a lot of material challenges. It's still a very hot area of research, just in case you're interested. Okay, so with that, we will wind up today's lecture. So we are done with compound semiconductor technologies. We'll finish here. Your compound semiconductor technologies, gallium arsenide, gallium nitride, the two major technologies I have touched base. There's a wide variety of things. Oxides are there, perovskites, there is antimonides, mercury, cadmium tellurides, and so on. It's not possible to cover everything within one single course. For that, we need a separate course on compound semiconductors. There's a lot of applications in optical devices and other areas, sensors and other things. I kept it only brief here in the purview of this course. Best introduce you to gallium arsenide and gallium nitride technologies, the very basics. Even in gallium arsenide devices or gallium nitride LEDs and HEMTs, there's enormous amount of content that you can just Google up and try to see. You can always email me or ask me if you have any questions. These are not actively a part of your curriculum for GATE exam or other exams if you're looking at, but these are important for your own understanding, for your curiosity, and for general awareness in the subject if you want to take up higher studies or you want to do in some government research labs and so on. Okay, so with that we will conclude our compound semiconductor class. From the next class we shall begin optical devices starting with solar cells. Okay, thank you.